In this video, I'm going to continue talking about quadratic functions, where I'm going to start with vertex form and then derive standard form. In my previous video, I discussed the example f of x equals a negative 1/3 times the quantity x minus 3 squared plus 2. We saw that from this vertex form, we can easily see what the vertex is, hence its name. And so here the vertex is the point 3, 2. So when x is 3, y is 2. We also found the y-intercept. The y-intercept is what you get when you set x equal to 0. So when we plugged 0 in here, negative 3 squared was 9, divided by negative 3 was negative 3, plus a 2 gave us negative 1. And then when we set to find the x-intercepts, we set the whole function equal to 0, and we found that whenever y was 0, there were two values that occurred: 3 minus root 6 and 3 plus root 6. What I'm going to do now is convert this to standard form and show you where we found these from, and in so doing, we'll talk about how we can find all these items from a function in standard form. So how do we get to standard form? Standard form is what you get when you expand your vertex form. That means this squared term is going to be multiplied out. We're going to square it, divide through by the negative 1/3, combine like terms, add the 2. So start by expanding the squared term. So we're going to have the negative 1/3 here, and we want to multiply x minus 3 by itself, which we do by foiling or using a shortcut, but it's all foiling. So negative 1/3. So what we're going to get here, we have our x times our x gives us x squared. Our negative 3 times the x, well, let's do that better. Let's do that a little bit better. X times x is x squared. X times negative 3 is negative 3x. That will be our first terms and our outside terms. Inside term, another negative 3x. And our last term, negative 3 times negative 3 plus 9. Notice two inside terms are identical, so we get twice the negative 3x. So we have a negative 1/3 times x squared minus 6x plus 9 and the plus 2. We need to distribute the negative 1/3. So negative 1/3 times x squared gives us a negative 1/3 x squared. Notice that's the a here. Negative 1/3 times negative 6 gives us a positive 2x. Negative 1/3 times 9 gives us negative 3. Then we have to add this 2 here. So in standard form, what we have is f of x equals a negative 1/3 x squared plus 2x, combine the constants to get minus 1. And here is the standard form of our function f of x equals negative 1/3 times the quantity x minus 3 squared plus 2. Standard form, you see, is the form ax squared plus bx plus c. So let's write that out. In general, standard form, ax squared plus bx plus c. Notice that the A in the vertex form, in this case 1/3, is the same thing as the A in the standard form, right? Because that's still 1/3. We see our B is 2 and our C is -1. Recall, our y-intercept was -1, and that's what happens when x is 0. So if you're in standard form and you evaluate the function at 0, the squared term cancels out, the x term cancels out, and all you're left with is c. So the y-intercept in standard form is the point 0, c, right? So here, this -1, that is the y-intercept. So when we're in standard form, you can't immediately see the vertex, but you immediately see the y-intercept. Well, how are we going to find the vertex and the x-intercepts? Well, let's start with the vertex. And remember that the vertex has the coordinates hk. Let's now take our vertex form in abstract form here with the h's and the k's, h, k, and a. Let's do the same thing as we did with our example and expand this. So I'm going to erase this, and we are going to expand the general vertex form. And then we can compare that with other things we know. Okay, so f of x equals a times, so we need to expand x minus h squared by doing x minus h times x minus h and add the k. Again, we FOIL x squared minus hx minus hx plus h squared plus k. Distribute the a. Oh, let's combine those like terms first. So remember, we end up with x squared minus 2hx plus h squared plus k. Now we will distribute the a. Ax squared minus 2ahx plus ah squared plus k. And compare that with the standard form written as ax squared plus bx plus c. The constant term has no x in it. So this here, this ah squared plus k, all simplifies to a single constant we call c. But we don't care about that formula. What we're interested in is this right here. Notice that the coefficient of the x term, which is equivalent to b, is -2ah, where h is the x-coordinate of the vertex and the axis of symmetry. So let's set those equal to each other. Negative 2 AH equals B. We want to solve for H. So to solve for H, we have to divide both sides by the negative 2A, and we get H is negative, I'll just put the negative in front, B over 2A. H equals negative B over 2A. That is the x-coordinate of the vertex as well as the axis of symmetry. So when you have f of x equals ax squared plus bx plus c, you can find the axis of symmetry as well, which is the x-coordinate of the vertex, by computing negative b over 2a, where b is the coefficient of the x term, a is the leading coefficient. So if we look at our function here that we have in standard form, negative 1/3 x squared plus 2x minus 1, and we're trying to find this 3, right, which is our axis of symmetry, x equals 3, x-coordinate of the vertex, then we can find it doing negative b over 2a. So a is a negative 1/3, and b is 2. If we go x equals negative b over 2a, we have a negative over a negative, so it will be a positive. It's good. We can even cancel the 2's, but instead of canceling the 2's like that, let's think of this as a division problem, because when I multiply the 2 and the negative 1/3, I get a negative 2/3. So I'll have over here x equals negative 2 over negative 2/3. Fraction bar is division, so let's have x equals negative 2 divided by a negative 2/3. And division is defined as multiplication by reciprocals. So here's where I can cancel the 2's and the negatives so that I am left with 3, just like we knew we should. So negative b over 2a gives us the axis of symmetry and the x-coordinate of the vertex of 3. How are we going to find the y-coordinate, the 2? Well, remember, the y-coordinate is simply the value of the function at the x-coordinate, right? Y is f of x. Okay, this now is going to be our k when the vertex, for the vertex hk, right? Vertex form, our vertex is hk. So if our x is 3, we just need to find f of 3. So f of 3 is negative 1/3 times 3 squared plus 2 times 3 minus 1. Well, 3 squared is 9, divided by negative 3 is negative 3, plus 2 times 3 is 6, minus 1. 6 minus 3 is 3, minus 1 is 2. So there's the 2, the y-coordinate of the vertex. So we have our vertex as 3, 2, like we should. And so we can generalize and say that when we have standard form, ax squared plus bx plus c, let's write it here, standard form, f of x equals ax squared plus bx plus c. Then the axis of symmetry which is also the x-coordinate of the vertex, is given by, let's go ahead and call that h, negative b over 2a. The y-coordinate of the vertex k is a function evaluated at negative b over 2a. Or we can simply say that the vertex is negative b over 2a, comma, f of negative b over 2a. So you really just need to worry about this negative b over 2a. All right, good. So we take care of the vertex. We already took care of the y-intercept. Now it's all about the x-intercepts. So we know that to find x-intercepts, we have to set the entire function here equal to 0. So that means we have to take our negative 1/3 x squared plus 2x minus 1 equals 0. We're not going to use the square root method because it's not already got the quantity x minus h squared anywhere that we can isolate it. We got x here and x here. So we could complete the square, but instead of doing that, let's use the formula that results from completing the square. So instead of doing the process, we'll just use the formula that's a result of the process. And I'm not going to derive that for you. You can find that in other videos from other people. But that's the quadratic formula. So we're going to use the quadratic formula to solve this quadratic equation. And the quadratic formula says if ax squared plus bx plus c equals 0, then you can find x by computing negative b plus or minus the square root of b squared minus 4ac all over 2a. Now notice here, this has a common denominator of 2a and two separate terms in the numerator. If I break this up, negative b over 2a plus or minus the square root of b squared minus 4ac over 2a, we see that this first term is the formula for the axis of symmetry that we just found, that we just derived. Right? We had already stated that if you're in standard form with ax squared plus bx plus c, then you could find the vertex by using negative b over 2a, and then plugging into the function to find the y-coordinate of the vertex. And then here it is right here. So the vertex, or the x-coordinate of the vertex, is also our axis of symmetry. So we are adding and subtracting this value to the axis of symmetry. Now, look what we had here as our x-intercepts that we found in the previous video when we were solving the vertex form using the square root method. 3 minus root x, 3 plus root x, where 3 is the axis of symmetry, right? X-coordinate of the vertex. So we were adding and subtracting root 6. So our axis of symmetry was 3, and we had to add and subtract root 6. And here is the root 6 we can find using the square root of b squared minus 4ac all over 2a. Let's go ahead and do that. So let me clear up some room here. So we already know the negative b over 2a part is 3. Let's focus on the square root of b squared minus 4ac all over 2a. And before we continue, let me just say something about b squared minus 4ac. This is a term that is called the discriminant. It has its own name because it's important. Notice that if this discriminant equals 0, then we are not adding or subtracting anything. So we just have our axis of symmetry, okay, is also V1 x-intercept, which means that the vertex touches the x-axis. So when this equals 0, you only have one x-intercept, which is the vertex. So the vertex is on the x-axis. Now, if this is positive, then because of this plus or minus, we get two x-intercepts. And these are real solutions. Only real solutions will show up on a graph, so two real solutions, two x-intercepts. And that's what we have here, because 6 is positive. We can take the square root of that to get two answers. And then if it's less than 0, then there are no real solutions, meaning that the graph did not cross the x-axis. No real solutions, no x-intercepts. Graph did not even touch the x-axis. In that case, the graph would be completely above or completely below. Right? Well, we've done this before. We know that we should get 6 for our piece here, square root of b squared minus 4ac all over 2a. So let's confirm that. Let's confirm that we get 6. B is 2. So we have 2 squared minus 4. A is a negative 1/3. C is negative 1. So that's the radical part, or the radicand. And then in the denominator we have 2a, which is 2 times negative 1/3. So this is, it's a little messy with all those fractions, but not that big a deal. Let's go ahead and solve this. And first I will go ahead and do it using all the rules of roots. And then we'll just see how we could do it just doing the calculator. So we have plus or minus the square root. 4, negative times negative times negative, minus, let's see, 4/3. That's all over negative 2/3. Because of this plus or minus piece, I'm not going to worry about signs. Four minus 4/3. Well, to get a common denominator, we get 12/3 minus 4/3 all over 2/3. Square root of 12 minus 4 is 8. 8/3 divided by 2/3. Okay, so 8 is 4 times 2. Square root of 4 is 2. 2 is under the radical. So we have 2 root 2. And this 3 I'll just keep under the radical as root 3. Now remember, this fraction bar is like a division. So we're dividing by 2/3, which is multiplying by 3/2. So that cancels. And we have 3 root 2 over root 3. Then if we rationalize the denominator by multiplying by root 3 top and bottom, root 3 times root 3 becomes 3. Root 2 times root 3 gives us root 6. There's the 3 out front. They cancel. And there's that root 6. A lot of work to get it, though, doing this. However, in practice, if you're not doing this, like for class, but this is actually a practical application, you could simply pull out your calculator right at the beginning and compute 4 minus 4/3 all divided by 2/3, and then not even worry about all this arithmetic, fractions, properties of square roots, rationalizing. But you simply put this into your calculator and computed the square root of 4 minus 4/3, or 4 divided by 3. Get outside the radical, divided by parentheses 2/3, or 2 divided by 3. And we get, as we saw before, 2.45. So we have 3 plus or minus the 2.45, and in the previous video we saw those were equivalent to 3 minus 2.45 or 0.55, 3 plus 2.45 or 5.45, and this is equivalent to 3 minus root 6 approximately to 2 decimal places, and this one, the 2 decimal places, is 3 plus the root 6. So whenever you're working with standard form, takes a little bit more work to find the x-intercepts, but you're going to just simply use the quadratic formula. And if you're doing this for a practical application, you can just use your calculator and get decimal approximations, and you don't have to worry about all that simplifying to get the radical. Now let me draw a picture that puts this together. I've already mentioned it, but let me go ahead and do a general graph, not for our specific example, but just kind of in general, that demonstrates the relationship between the quadratic formula and the graph of a quadratic function. So in standard form, f of x equals ax squared plus bx plus c Let's clean this up. Let's try to draw this. All right, so our axis of symmetry, x equals negative b over 2a. This one I'll go ahead and draw opening up. All right, so here's our vertex. Where the x-coordinate is the same as the axis of symmetry, the negative b over 2a, and then the y-coordinate is found by evaluating the function at the negative b over 2a. I will put our y-intercept here at c. Try to draw a parabola. And then our x-intercepts here are equidistant from the axis of symmetry. Where this distance here is the square root of b squared minus 4ac all over 2a. So both these pieces combine to form the quadratic formula, where we say that if you're given a function in standard form and you want to find the x-intercepts, that would be the same thing as solving the quadratic equation ax squared plus bx plus c equals 0, then x is found by finding negative b over 2a plus or minus the square root of b squared minus 4ac over 2a, but it's usually written all together as negative b plus or minus the square root of b squared minus 4ac all over 2a. So hopefully that helps you graph functions in standard form, but also understand how the quadratic formula relates to the graph of a function in standard form, and how you can use the quadratic formula to find your x-intercepts. So thank you for watching.